explaining an amazing article from Carnegie Mellon University. The joint extraction of events and entities within a document context. So this amazing article by people in Carnegie Mellon University. So it looks at it at a document level. So this is the ACE data set that it has 529 documents, around 14,000 sentences and about 4,000 triggers. So the standard methodology is just, as I said in the previous lecture, just single sentence, single trigger. Everything is simple, just like semantic role labeling. Everything is very simple. But if you want to improve it and generalize a little bit to consider more than one triggers inside your sentence or multiple sentences, then you need to model the relationship between even different triggers. For example, this is trigger 1, this is trigger 2, and each one they have their own set of mentions. And so it's a graph. You can model it as a factor graph as well. I love factor graph because it's a very natural. So factor graph is really amazing, just like deep learning. For example, classical deep learning, we work in the continuous space, continuous domain. But in factor level and graphical models, we usually, because we want to be tractable, we usually try to work on the discrete level, which we can use the amazing power of computer science, discrete mathematics, all of linear programming, all of discrete math that we know, like approximation algorithm that I have explained in a playlist for approximation algorithm. So it has a very rich mathematics, and it is fast. You don't need to get involved with the curse of dimensionality and those things. So deep learning one day should meet these discrete math. Let's say continuous domain should meet the discrete and somehow regulates, like Central Bank of America regulates everything. We need a regulator in this world. So the continuous domain is very rough. It could be anything. It has problems of curse of dimensionality. The discrete domain is very cute, and so it's very cute, but it doesn't have power. So they should work with each other, the discrete domain and the continuous, and going back and forth in order to create a rich mathematics, rich theoretical background for machine learning. And so this is a methodology that causes errors. If you just look at one sentence, one trigger, it has some problems. So most existing work extract events independently, which is very bad because they ignore the rest of the documents. And a better methodology is to first decompose the learning problem into 3 tractable sub-problems, learning the dependencies between a single event and all its potential arguments. So this is a trigger. This is its arguments. Then we have another trigger and another set of arguments, but we also connect them as well. And these could be lots of them. So it's a beautiful graph. So a better methodology will propose a structured model for learning within event structures, and then we introduce joint inference. So everything is joint. We add all of these losses because they interact with each other. And we conduct extensive experiments on ACE corpus, which is expensive, of course. And so there are different types, as you know, for entity mentions or location or organization. This is entity. You can use CRF, conditional random field. I have used conditional random field and LSTM in my article because they are important. And 2 important notes. Not every entity mentioned in the sentence is involved in events. A single entity mention can be associated with multiple events. So this distinguishes this with the rest of the articles in the literature. So this is a notation. You see, this is just, these are factors, factor and then ordinary node, then factor, then ordinary node. So so it's a factor graph, and I have a playlist for factor graphs and structure predictions and graphical models. So I assume that you know what is factor graph and you have watched that as well. So this is we have this trigger, we have this trigger. Each one has some of our arguments. They have some labels, and we want to extract to think about it like this, because this T, for example, this is trigger, one trigger. It is related to entity with this relation, and this trigger could be connected to another. So I've explained it in this like this. For example, if you omit this line, so it's a complete graph, because we are learning within event structures. This is within event. We are learning event, so event. Learning entity extraction, so this is entity extraction using conditional random field. So if we combine all of these losses, we have a very mature and rich model. And it's like human level understanding, because human, they consider everything holistically, all of them at the same time. We don't say that we model entities independently. We don't do that usually in our brains. Our brains sees everything, considers everything simultaneously. Learning within event structure, so we can model what is the probability of this trigger given your I and your neighbors. Your trigger candidate I and your neighbors of your trigger candidate I. So we model it. So because they have different combinations, either this one, either this conversion, so it's better to model it as the different weights. It has different weights. So the features are unary features functions, the dependent trigger, like or binary. So there are different combinations. So there are features for trigger, for argument, for entity. And so the training, you just add, of course, for regularization that we do in machine learning. But the important thing is this, that we will talk about it. So given a trigger candidate per I and I prime, for example, I and I prime, and each one has some of its attributes, and also they have a relation between them we should model. So it's a very complex factor graph if you model it with factor graph like this. And so we just learn it, and you know, for inference we use that some product algorithm that I have explained in the playlist for structure prediction in graphical models. So the entity extraction, we just use CRF. It's very, very good. But we are not working on that independently. We add the loss together. We model them jointly, everything together, just like the human brain. And so this is the when E can be further decomposed. So this is for E, this is for relation, this is for all entities, and we combine them together. For example, D could be the probability, a marginal distribution derived from the linear chain of conditional random field. And so there we have three different things. Within the sentence, between the triggers, and finally for the entity mentions. So for joint inference, we can use, they use dual decomposition, they combine dual decomposition and augmented Lagrangian in this article. Whenever you have some kind, as I have explained under my place for approximation algorithm, whenever you have some discrete problem the main methodology is just to relax it and consider discrete as a continuous thing. So we do everything classically, Lagrangian and everything, which is continuous. And then we come back to the original domain, which is discrete, in order to understand how these graphs are related. Because when it is one, there is an edge between them. When there is no edge between them, we prune it. And so this is either 0 and 1 in the classical linear programming. And there are amazing results on that. So the results for spurious or misclassified or missing. What is interesting is that for event trigger, we have separate. You see, the precision is relatively good. Recall and the F1 score. This is the things that we need to measure our algorithm if it is better than state of the art. So we should outperform these state of the art models. And so for each of them, for event trigger classification, we have a different set of F1 scores. For event argument identification, for argument role classification. And this is a great book. If you have time, you can read this amazing book. And discrete latent structure in neural networks.